Reducing radical numbers is as straightforward as reducing rational numbers. It just has an algorithm associated. And before we start, let's talk about or remind ourselves that a radical number is a number that has this symbol. And to reduce it, you've done a little bit of this in the past. The number or the square root of 36, this is easily reduced because 36 is a perfect square. This reduces to 6. But what do you want to do if you're looking at the square root of 72, for example? This number is easy to reduce. It's not a perfect square, so I'm not going to end up with an integer when I'm finished, but I'm definitely going to end up with something easier to work with. So let's start with 36, the square root of 36. And even though you know, just because you know that that equals 6, let's look at why it equals 6. So the square root is really the opposite operation of squaring. So if I were to take 2 squared, that equals 4. But the opposite direction would say the square root of 4 equals 2. Now granted, in the opposite direction you lose the square or you add the symbol, so they look slightly different, but you can kind of see how they're the same-ish operation, right? So let's look. If I take 36 and I'm going to factor it, hockey stick method, divide 36 by 2, I get 18. Divide 18 by 2, I get 9. Divide 9 by 3 and I get 3. So the product of primes is 2 times 2 times 3 times 3, which is the same thing, and you should be pretty good at this by now. I can write this as 2 squared, and 9 can be written as 3 squared. And you can almost see the relationship that the square root of 2 squared just makes sense that that would be 2, times the square root of 3 squared would be 3. Now, I assume that seemed a little bit magical and hand-wavy to you. Trust me, very soon in the semester we will make more clarity out of what just happened, but I'm hoping that you can get a hang of or just see the logic that the square root of 2 squared should be 2, that makes sense, and that the square root of 3 squared should be 3. They even sound like that would be correct. So at this point, I just want you to go with your guts a little bit. We will get there to the more algebraic understanding. But because of that process, using the product of primes, we can create an algorithm that you can follow to get to good answers. And your brain will begin to gather up the pattern recognition part of it and start to make some real sense of it. So 2 times 3, to get back to the problem, is 6, and that's indeed where we were before. So now let's look at 72. We know 72 isn't a perfect square, and so we know that it's not going to result in an integer solution, or it's not going to reduce to an integer, but hopefully we can make it a smaller, prettier number to work with. I'm going to start again by factoring product of primes using the hockey stick method. I divide 72 by 2 and I get 35 36. Divide 36 by 2 gives me 18. 18 divided by 2 gives me 9. 9 divided by 2 is 3 times 3. So in this case, I have 3 2's. It was easy when I had 2 2's to see that one of them was going to come out of the radical, and 2 3's was going to send one out of the radical. But this time I have 3 2's. Not a big deal. I'm just going to take 2 2's and pull them out of the radical just like I did here, because this is 2 squared, and so the square root of 2 squared is just a simple 2. I can go ahead and pull my 3's out of the radical, but this 2 is all by itself. It's not the square root of 2 squared, it's just the square root of 2. So that has to stay up underneath. And so we get 6 root 2. So it's a simple pattern that you just follow the rules on, and you get to something much easier to work with. And you can certainly see that 6 times the square root of 2 is much easier to handle or to deal with than the square root of 72. So let's look at a couple more just to get a feel for the algorithm. How about the square root? I'm probably going to regret this, making one up off the top of my head, but let's see. The square root of 126. I promise if it gets too ugly, you'll never know what happened because I'll back up the tape and do something else. So let's reduce the square root of 126. So what we want to find is pairs that we can pull outside of the radical. So let's do that by factoring. We divide 126 by 2 and we get 63. I'm going to divide 63 by 3 and that gives me 21. 21 divides by 3 giving me 7. So let me double check my arithmetic real quick. 126 is 63, correct. Divide 63, 6 divides by 3, leaving 2, and 3 by 1. Yep, that's good, and 3 times 7. So in this case, the only thing I have a pair of, the only thing I can take out of the radical is this 3 times 3, because remember, this equals 3 times 3, which is the same thing as 3 squared, which means the square root of 3 squared can simplify out of the radical as just a 3, and then I'm left with 2 times 7 inside. So I have the square root of 2 times 7 is 14. Even though 3 times the square root of 14 isn't necessarily nice to look at, it is better than the square root of 126. So let's try another one. Let's do 588, and we want to reduce the radical. So again, 588 divides by 2, leaving 250 plus 40 is 294. That divides by 2, leaving 145, 46, 47. I think 147 divides by 3. 3 times 4 is 12, leaving a 27, and 3 times 9 is 27. And then 49 is 7 times 7. So what do I have pairs of that I can pull out as separate factors or as individual factors? I have a 2 squared, which comes out of the radical as a 2. And I have 7 squared, which comes out of the radical as a 7, and I have this 3 that has to stay inside. So 2 times 7 is 14, root 3. Okay, let's do one more. I just feel like we should do one more. How about, what have we done already? How about the square root of 24? So we'll take the square root of 24, divides by 2, leaving 12, divides by 2, leaving 6, divides by 2, leaving 3. I have a pair of 2's, a 2 squared that can come out. The square root of 2 squared is simply 2. And then inside the radical, I have to keep a 2 times 3, which is 6.